In this research paper titled, Evaluating Multi-Hop Reasoning in Large Language Models, a chemistry-centric case study, the authors, including Mohammad Kodadad, Ali Sharaeh Kazmi, and others from McMaster University and BASF, explore how well large language models handle complex, multi-step reasoning, specifically in the field of chemistry. They focus on what's called multi-hop reasoning, which means connecting multiple pieces of information across several steps to answer a question, something that's crucial in scientific domains like chemistry where knowledge is interconnected. The study introduces a new benchmark designed to test these capabilities. They created a curated dataset and an automated evaluation process to assess how large language models, or LLMs, perform in compositional reasoning within chemistry. Compositional reasoning involves breaking down and recombining information in logical ways, which is often a weak point for even the most advanced eyes. To build this benchmark, the researchers developed a fully automated pipeline that's been verified by experts in the field. This pipeline starts by using OpenAI's reasoning models, like O3 Mini and GPT-4o, combined with named entity recognition, or NER, systems. NER is a technique that identifies and extracts specific items from text, such as chemical names or compounds, from recent scientific literature. Once these chemical entities are extracted, the pipeline augments them with information from external knowledge bases. This creates a comprehensive knowledge graph, which is essentially a network of connected facts and relationships in chemistry. From this graph, they generate multi-hop questions that require multiple hops or steps to answer, like linking a chemical reaction to its properties and then to an application. The evaluation tests LLMs in two main settings. One where the model has access to additional context, like retrieved documents, and another where it doesn't. Their experiments show that even top-tier models struggle significantly with this kind of multi-hop compositional reasoning. For instance, the results highlight that while augmenting LLMs with document retrieval can greatly improve performance, it's not a perfect solution. Even if the retrieval is 100% accurate and provides full context, reasoning errors still occur, pointing to the inherent complexities of putting together multiple pieces of information. In the introduction, the authors note that LLMs have made big strides in various tasks, but multi-step reasoning remains a challenge. They mention techniques like chain-of-thought prompting, which encourages models to think step by step, as seen in works from researchers like those referenced in the paper. Innovations from OpenAI's O-series and open-source models like DeepSeek R1 have tried to scale this up, using things like reinforcement learning to refine reasoning during training. However, these improvements are mostly in general areas like math or coding, and scientific fields like chemistry haven't been as thoroughly tested. The paper points out that existing benchmarks for multi-hop reasoning, such as Hotpot QA or Strategy QA, are more general and don't dive deep into domain-specific areas. In chemistry, where you need to integrate specialized knowledge, this is a gap. Previous works have touched on subfields like reticular chemistry, but the authors argue for more comprehensive benchmarks. To address this, their automated pipeline is a key innovation. It uses OpenAI models to extract entities, build the knowledge graph, and generate question-answer pairs. This not only creates challenging datasets for chemistry but could be adapted to other domains, making it a versatile tool for generating unlimited reasoning datasets. The contributions of the paper are clearly outlined. First, they provide extensive evidence that compositional reasoning in scientific domains is still a major limitation for current state-of-the-art LLMs. Second, they demonstrate through experiments that even with perfect retrieval augmentation, errors persist due to the complexities involved. Third, they introduce this automated pipeline for knowledge graph construction and multi-hop data generation, which leverages NER and AI models. Finally, they contribute a new benchmark specifically for multi-hop question answering in chemistry, and they've made the full dataset and evaluation code publicly available for others to use and build upon. In the background section, the paper discusses how multi-hop question answering has become a standard way to evaluate ILM's reasoning abilities. It requires integrating evidence from multiple sources, and traditional datasets have evolved to include various domains. The authors reference related works that show how recent advances in scaling reasoning have helped, but models are still mostly general purpose and not optimized for scientific specifics. Overall, This research underscores the importance of developing better tools and benchmarks to push LLMs forward in handling real-world, domain-specific challenges. By focusing on chemistry, it advances our understanding of computational linguistics and highlights areas where AI still falls short, encouraging future work in more specialized reasoning tasks.